In this video, we're solving problem 4.7.14 from Nagle's Fundamentals of Differential Equations with Boundary Value Problems, 7th edition. We're asked to find the general solution to the given Cauchy Euler DE for t greater than 0. This problem appeared on quiz number 4 from the spring 2021 semester in Elementary Differential Equations at Tulsa Community College. Now, I want you to notice that the power of t and the order of the derivative multiplying it in each of these terms are the same. That means it's Cauchy Euler. Here we've got a t to the 0 and a 0th derivative. So for Cauchy Euler equations, we're going to let our variable, our dependent variable, in this case y, equal t, and our independent variable, raised to the mth power. And since it's second order, we're going to compute the first and second derivative, and then we will substitute into the differential equation. So we'll let y equal t to the m. Y prime by the power rule is m times t to the m minus 1. Y double prime, you bring your constant down, bring your power down, multiply by t to the 1 less power. If you want, you can distribute the m here. And then we're assuming that y is a solution to this differential equation. If y is a solution to this differential equation and y is equal to t to the m, then these functions have to satisfy that equation. So we will substitute into that equation, and this is what we'll get. We'll have t squared times y double prime, which was this expression here, minus 19t times y prime, which was m times t to the m minus 1. And then 100 times y, which we assumed was t to the m. Since y is assumed to be a solution, when we substitute in, we should get a 0 on the right-hand side. Now, whenever we're multiplying powers of t, we've got to add the exponents, because it's like we've got m minus 2 copies of that over here, and we've got 2 more over there. You're asking yourself, how many copies do you have? Well, you've got this many plus the extra 2. So when we add the exponents, that gives us the right number of t's, so we have t to the m there. Similarly, because of this t to the first here, because of the form of the Cauchy Euler equation, this power of t compensates for that decrease in the power of t that happened when we took the first derivative. So when we multiply these together, we get m minus 1 plus 1 for our exponent. That's going to be a t to the m as well. So all of these guys have a factor of t to the m. Let's factor that out. And then let's see what's left. T to the n times this quantity m squared minus m gives us the first term. And t to the m times a negative 19m gives us the second term. And t to the m times 100 gives us the last one. This times this equals 0 if this equals 0 or this equals 0. And this is never 0 because we're assuming t is greater than 0. So we must have m squared minus 20m plus 100 equals 0. That's our characteristic equation. The values of m that satisfy this equation cause t to the m to be a solution of our differential equation. This actually factors pretty easily. I need two numbers that give me a product of 100 that add to 20, or negative 20, excuse me. 10 and 10 will work, if they're both negative. A negative times a negative is going to be a positive. It's going to give me a positive 100. And negative 10 plus negative 10 is negative 20. So we actually have a repeated root. This is m minus 10 squared equals 0. And that means we've got two values of m that are exactly the same. This equals 0 and m equals 10. Okay, great. And the corresponding solutions are t to the m1, or t to the 10th in this case. And the second linearly independent solution can't just be t to the m2, because that would be t to the 10th, and that would not be linearly independent from y1, which is t to the 10th. So we have to multiply by an extra something. With constant coefficient equations, we always multiply by an extra x or an extra t. But with Cauchy Euler equations, when we have a repeated root, we multiply by an extra natural log of t. And then once you have your two solutions, y1 and y2, the general solution is just a y equals c1y1 plus c2y2. So you have c1 times t to the 10th plus c2 times t to the 10th times natural log of t, and that will work on 0 to infinity. Okay, that is how we solve that equation.